Okay, this lesson is on binding energy and Einstein's famous equation, E equals mc squared, definitely his simplest one that we know of. What we're taking a look at is the difference between what the true atomic mass of an oxygen atom's nuclei is, and what the theoretical mass should be. Now, if the true atomic mass of an oxygen 16 nuclei is 15.99492 atomic mass units, what amount of mass has been converted to energy to bind the nucleus, and what is the binding energy per nucleon of oxygen 16? So what happens is, whenever a nucleus is formed, some amount of matter, a very small amount of matter, is actually converted to energy, and that energy we call binding energy, and that energy would be released if we were to separate nucleons, either protons or neutrons, from the nucleus, and that would be in a nuclear reaction. So it turns out that whenever a nuclei are formed in a nuclear reaction, there is a tiny bit of matter that's actually converted to energy. And the force that holds the nucleons together is what we call the strong force, or the nuclear force. And that overcomes the repulsion between the positive protons. The neutrons are in there to sort of give some space to space out the protons from each other, but there's also a force that holds the nucleus together. Now, Einstein came up with his equation that says if we take the mass of the any object that's been converted to energy, we take that mass in kilograms and we multiply it by the speed of light squared, that would tell us how much energy would be converted from mass. It's speed of light is 3.00 times 10 to the 8th, so you square that, you get 9.0 times 10 to the 16, which is a pretty big number. So even a small amount of mass would have a massive payout in terms of energy. So this is oxygen 16, and that's our atomic mass unit. So what we need to ask ourselves is what would be the theoretical mass of oxygen, or what should it be? Now, a proton actually has an atomic mass of 1.007277 atomic mass units. And in oxygen, we have 8 of those. So we would take this number and multiply it by 8 to give us the theoretical mass of all the protons. Then we'd also have to add in our neutrons, 1.008665 atomic mass units. Multiply that by 8. That now add the two together, we have the theoretical mass of the nuclei of one oxygen atom. So when we put those together, we get 16.127536 atomic mass units. Obviously, a difference between those two numbers. So a small amount of matter has been converted to energy, and that would be the binding energy. So let's figure out what that difference in mass looks like. So we take our theoretical, which is a larger number, subtract it from the actual, and as you can see, we get a number 0.13261 atomic mass units. So this will tell us the binding energy of the entire oxygen nucleus. Or we can use this, to figure that out. So what we need to do is figure out the mass in kilograms of that difference, and then multiply it by the speed of light squared. So this is where some trickier arithmetic comes in here. We take our mass in atomic mass units and we multiply by a factor, 1.6606 times 10 to the minus 24. That's how many grams are in one atomic mass unit. So we multiply these two things together, and that'll tell us the difference in mass in terms of grams. But for Einstein's equation to work, we have to convert that one more time into kilograms. So we multiply by a factor of 1 over 1,000. 1 kilogram requires 1,000 grams. So we multiply these two things from our difference in mass, and that will tell us our difference in mass for one atom of oxygen between the theoretical and the actual atomic mass in kilograms. And here's our speed of light. So when we do all that, we get this number. Not a lot of energy, pretty small, but that's considering that's only one atom. And that's just the energy that would be released if we were to split the entire atom apart. Now, most nuclear reactions, you don't actually split the entire atom apart. You might knock off some neutrons or protons, but you typically don't obliterate the entire nucleus into all of its parts. So let's take a look at the binding energy per nucleon. So to get that, we take the binding energy that we calculated, and we divide it by the number of nucleons in the nucleus. And this is both number of protons and neutrons. It's oxygen 16, so obviously we have to take our binding energy and divide it by 16. And we get the following number, 1.239 times 10 to the minus 12 joules per nucleon. So if I were to kick out one neutron or one proton from an oxygen 16 nucleus, that's how much energy would be released. Put in a perspective, helium, which is pretty low in terms of it's got one of the lowest amounts, is 1.14 times 10 to the minus 12 joules per nucleon. What you'll notice is that these numbers right here will continue to rise until we hit iron, and iron has the highest binding energy per nucleon. It's got the most stable nucleus, it's the most dense nucleus, and if you have really, really, really big stars, once they start fusing nuclei to make iron in the core, that's when your star dies and it goes into supernova, because you cannot fuse anything to iron's nucleus to make any larger elements within the confines of a fusion reaction in a star. However, all the other elements that are formed happen when the star goes supernova. When the star's fusion reactions stop because the core is now filled with iron and it can't fuse anymore, gravity takes over and pulls all that mass of the star, and these are stars 10 to 50 to 100 times larger than our sun, pulls all that mass into one tiny little point. And that could happen in 100 seconds, or it could happen in a couple months depending on the size of the star. But it happens pretty quickly, and in that time, all the other elements larger than iron get formed. It takes millions and billions of years to make all the other elements in the core, but it takes only the blink of an eye to make all the rest of the heavier elements. Once you go past iron, your binding energy actually starts to decrease, which is why the really, really heavy elements have a low binding energy per nucleon, which allows them to undergo fission reactions like uranium, which has a lot less binding energy per nucleon than iron would. Anyways, there you go. There's a practical component to Einstein's equation.